Hello everyone. This particular video is going to be something of a review, but more importantly a demonstration on what buttons to click in Excel to perform correlation and regression analysis. There was a PowerPoint presentation that kind of went over this, but I figured since we have the power of live video now, or I guess not live, recorded video now, where I can demonstrate what actual buttons to click, that perhaps it would be useful to go do that. So here we have a data set, one of the remaining student-submitted data sets on Alaskan fish counts. And so this is what we're going to use to do our correlation and regression analysis. On the first column, so column A, this will be our X variable, which is year, whole numbers. And then column B, we have our Y variable, the number of salmon in what is presumably a tributary of the Pilot River, maybe Pilot Creek, something like that, someplace in Alaska. We're going to do correlation and regression analysis. This is all about drawing straight lines through data and determining whether or not the data match a straight line and to what degree that match is good. Is it a statistically significant straight line? And that kind of thing. In order to do correlation and regression analysis, we have a few requirements. One of the most important ones, and going all the way back to I guess the third lecture on types of data. Both our X variable and our Y variable have to be either interval or ratio level. So they have to be real numbers. They can have decimals in them. They do not necessarily have to be continuous, but they often are. So year is, in this particular data set, they are discrete, so they are only whole numbers of years. But year is a subset of time, like the concept of time, which is continuous. Number of salmon can only be discrete, I guess, unless a bear got it, and then you could have partial salmon. But really, this is discrete. But that doesn't matter because they are real numbers with a meaningful 0 point. So this is still ratio level data, as is year. Well, year is interval level data. We do not have a meaningful 0. So these are both either interval or ratio level data, which is one of the main requirements for correlation and regression analysis. We can use some Excel functions to shortcut some of the analysis. Like if all we want is an r squared, and then we could use the equals correl function and then square it and get a number. But honestly, unless you are having to bust out a whole lot of these in very, very quick succession, you really want to look at your data. Visualizing data, especially when it comes to scatter plots, should pretty much always be the first step you do. So I'm not even going to bother going through the Excel functions here. We're just going to jump straight to the plot because you should really be doing that. So let's insert a plot. We'll do insert. We want to insert a scatter plot. And we want to insert a scatter plot just using the dots. We don't want Excel to put straight lines that connect our data points, and we definitely don't want it to put in curvy lines. So our data are whole numbers of years. I do not know what or how this number of salmon corresponds to that year. So is this a total number of salmon in a year? Is this the maximum number of sample in that year? Is it the number of sample during a fall spawning run, but maybe not the rest of the year? So at least without having followed the link to see what the deal with the data are, I don't know how the numbers in this year change from 1998 to 1999, like if there's a seasonal pattern that's going on. If there is, then it is a completely wrong thing, or we give the completely wrong impression to draw a straight line between 98 and 99 if in the winter the numbers actually go down and then they come back up again in the spring or the fall or whatever happening. Since we don't know what happens between this data point and this data point, we do not want to pretend we know by putting lines in there. So we're just going to stick with straight old data points. So let's put that in. We will right click, add select data. We want to add data, so we have something to plot. The series name only applies if we have multiple x's and or multiple y's. We only have one x and one y in this particular case. So we can skip series name. We'll go to the series x values. This is in fact our x values. otherwise known as our predictor variable, or what used to be the independent variable, but we don't really use that terminology anymore. Excel, for reasons I don't understand, automatically populates the series y values with this equal bracket number 1 close bracket. If you leave it there, generally it'll mess things up, so we delete it out of the way. And we highlight our y data. We can tell it worked because we now have data in our plot. These commas are something that Excel put in there automatically. They don't actually exist in the data, so the value that Excel is reading to put this plot in is just 54560. If you were to type this in by hand and put a comma, it would probably still work because Excel is smart enough to know that commas are thousands separators and not text. But be mindful of doing things like that. If these were actually text values, so words, for instance, words are not interval or ratio level data, so a scatter plot will not work for them. So I'll hit OK here. We're done with this. And there is our scatter plot. Formally, we should add an x-axis. The year is probably pretty apparent, but we should at least add a y-axis specifying what these are. In fact, perhaps we will do that just so I can be a good example. So this is year, and this is that. Now you learned a shortcut for doing y-axis stuff. Okay, we don't care about a plot title, so we'll just make our plot look a little bit bigger there. Okay, so here's our scatter plot. First thing we should do is eyeball it and do some checks and make sure everything worked the way we wanted it to. We wanted year to be our x. Year, in fact, is on our x-axis, and not just because we labeled that way, but we can see by the axis numbers on the axis, this is our year. And our y variable is, in fact, number of y salmon. The y is the number of salmon. It starts at 0 already, which it probably should. Has a max of 350,000. So that's kind of in the range of the data that we can see here, so that's probably right. As far as eyeballing trends, if we were to kind of follow the pattern over time, we may say that, yeah, it's going up here, and then it goes down here to 2010, and then it kind of stays more or less flat, maybe a slight increase going into present day. So it's doing all sorts of stuff. I would be hard-pressed to say there's an overall pattern one way or the other. I would guess that there is not, especially not a linear one. If we're going to allow curvilinear, so non-linear patterns, then sure, it went up and down, and maybe it's starting to go up again. So maybe there's a kind of cyclical pattern in the data overall. But in this class, we just focus on linear trends. Fortunately for us, statistics has given us the power to not have to just eyeball things, but we can get numbers that correspond to how strong the relationship is and whether or not it is statistically significant, meaning we can run a formal hypothesis test and get a p-value and reject or fail to reject the null hypothesis that there is a trend. There is a linear relationship between changes in year and changes in number of salmon. We can use some built-in Excel functions for that, but since we have a plot, we might as well just use the plot to do it. In order to do that, we put our cursor over one of the data points, right-click, add trend line. It defaults to a linear pattern. We can see it has already given us the best fit line, the linear least squares regression line. We can also see that the best fit line actually is not straight across. It does have a slight positive slope to it. Now, whether or not that is a statistically significant slope, so this is a sample of data. Because it is a sample, we have to use statistics to say, if we were to take lots of samples, would it still be positive? Or is it effectively 0 and this one particular sample happens to be positive? So this particular sample does happen to be positive, and we will calculate a p-value to determine how realistic that is, how significant it is. We do not want to set the intercept. That would take this point and stick it on 0. We don't want to force that to happen. We just want the line to stick with the data. We don't at this point have plans to interpolate, so to predict values within the data, within the range of the data. And we have no particular plans to extrapolate, to predict data outside of the range of our data. So we probably don't need the equation, but I do it anyway because it's here. It's not necessarily a bad idea either, because we can sometimes evaluate the y-intercept and see if it makes sense. So this is effectively saying, remember the y-intercept is the value of the y-axis when x equals 0. So x is year, so if we were to go back in time all the way to year 0, which has no particular meaning for us, then we are predicting there would be negative 2 million salmon. This is scientific notation, 2e to the minus 6. That is clearly a meaningless number. We don't have negative salmon, but it also doesn't really make sense to arbitrarily go back to year 0. 0 has no inherent meaning. So even though this is negative and doesn't make any physical sense, we're not particularly concerned about that because it also doesn't make sense to go back to the year 0. Let's go back to our line and also add something that we definitely do want to have, the r squared. Remember, r squared for us should be a lowercase r because capital R has a different meaning. It's really used in multiple regression when you have multiple x values that you use to predict a single y value. Excel is silly and puts a capital R even if we're just using one x and one y. Ultimately, it means the same thing. This is the coefficient of determination. This, expressed as a percentage, so 1.2% in this case, explains or describes the amount of variation in the y that we can be explained by variation in the x. So as we move across in years, the change in y, or that change in year, only explains 1% of the change in y. If you're thinking, wow, 1% does not sound like a very large amount, you would be exactly right. This is a very poor fit, and our change in year is doing a very bad job at predicting number of salmon, at least when we force those predictions to be based on a linear line. Again, if we could change this to a non-linear line, then perhaps and probably our square would go up and we would be doing a much better job at predicting things. So we have r squared. That's useful. That is kind of our go-to statistic for how good is our fit. But it doesn't answer the question on whether or not this line that is increasing slightly in our sample would also be increasing in the population sense. So is the true regression line increasing? Is there a true statistically significant increase or decrease over time? In this case, we're looking for an increase. So that is a question for a hypothesis test. Hypothesis tests have p-values, so we should calculate that. They also have t-scores, and they probably also have critical values, but we really didn't consider that approach. We just went straight for the p-value because it's the easiest. And we get a p-value based on the r statistic. So this r squared is the coefficient of determination. R is the correlation coefficient. And r is what we need to get the p-value. So first we should calculate r. So we'll put r here. And then r is going to be equal to, well, this is r squared. We just want an r, so we should be able to just take the square root of this. In fact, that is exactly what we do. We take the square root of 0.012, and that will give us r. Not very exciting. R squared can only be positive because it's a square. R can be positive or negative, and because we're taking the square root of a value that can only be positive, we have to look back at our line and determine whether or not R actually is positive or if we need to by hand stick a negative sign in here. Well, by eye, we can see that the slope is increasing. We can also look at the regression equation here and see that that first term, the one that has the x next to it, this is also positive. So the slope is positive, and so r also has to be positive. R is again, a very small number, which makes sense. R goes from -1 to +1. 0.1 is pretty close to 0, which would imply a nearly horizontal line. So we can see this is There's a lot of scatter, so again, the x-axis variable is not doing a good job of predicting our y variable, and so our correlation between the two is very poor. So that's R. From R, we need to calculate a t-score, and I have the t-score formula that relates to R up here. So we can type this in also. There's our t-score, and to calculate the t-score, we need R times the square root of n, and n is the number, not the number of data points, because remember we have x data points and y data points, but it's the number of pairs of data. The other way to think about that is it is the number of rows of data. So we have 22 rows of data here, but the first row is a header row, so we have to subtract that. So we have 21 pairs of data, 21 rows of data. So that is n, and I don't know what just happened there. There's 21 rows of data, and we need to subtract 2, because we lose 2 degrees of freedom when doing a regression. There's a mean of an x and a mean of a y that we have to take into account. So we subtract 2 from that. And then we divide by another square root here, and that is 1 minus r again, which we have over here, and we want to square that. In Excel, putting the caret is how we do exponential values. So we'll put in our caret, close one parenthesis, close two parentheses, and that should be everything. So we have a t-score that's, again, pretty low in the grand scheme of things. Most of the t-scores you've seen have been, for instance, 1.96 and 2.4, and one of the last problem sets had a minus 5.5. So 0.48 is quite low. And we can tell exactly how low that is by converting it to a p-value. Put it into, from distance units, distance from a mean, into a probability of seeing a slope, of seeing a correlation this strong or more extreme. So we'll put in p-value here just so we know what's going on. And then we follow this equation. So we've seen this one before in hypothesis tests. In order to do, or to get a p-value from a regression, we are doing what is really a two-tailed t-test. Or not a t-test, a two-tailed test using a t-distribution. So we want a probability, we have a distance in via the t-score. So that's what we put in, just like we did for hypothesis tests using the t-distribution. So t dot dist dot two-tailed. Here we need the absolute value of the t-score because that dot 2t doesn't understand negative signs. Our t-score is already positive, so we don't actually have to worry about that. And we'll just enter that in. And again, n minus 2, we said there were 21 data points. So let's just spell this all the way out. We said there were 22 rows, so 21 data points. Minus 2, because the degrees of freedom is n minus 2 for a regression, as mentioned before. Close all of our parentheses, and we see that the probability of getting a correlation coefficient this high, of having a slope that does this under this kind of condition, or something more extreme, is 0.64. So it is very likely to see a slope, to see data with this pattern under the condition that there actually is, or sorry, under the null hypothesis that the slope is actually 0. So if we were to resample this under slightly different conditions, but similar conditions, and keep on doing that, it is entirely possible that in reality there is no relationship between year and number of salmon, and that the relationship we're seeing just happens by chance. So same kind of interpretation for p-values as we've seen previously. We would fail to reject the null hypothesis, and the null hypothesis is no relationship between x and y. That's the same thing as saying the slope equals 0. And I think that is good enough here.